Hi everyone, this is object-oriented software development with C++, and in this lecture we will talk about virtual functions and polymorphism. These topics are related to pointers and some advanced features in object-oriented programming. Some of these might be needed for your coursework in case you wish to make it more advanced and related to the core functionality of C++ and object-oriented programming. So this lecture covers a rather loosely related collection of topics, including virtual functions, friend functions, static, no, not friend functions. We already talked about friend function earlier. We'll talk about static function and polymorphism. So let's first talk about virtual functions. So a virtual function, as you can see here, says virtual means existing in appearance but not in reality. Okay. When virtual functions are used, a program that appears to be calling a function of one class may in reality be calling a function of different class. So it may appear that you are calling a function that is a member function of one class, but you might be calling the member function of another class. So that's why it's called virtual. Virtual, as I said, means existing in appearance but not in reality. So how can you understand this stuff? Let's first look at an example. And after that, we'll try to explain why we need virtual functions. So in this case, you see 1, 2, 3 classes here. This is the base class, means it doesn't extend or derive any class. In this class, we have this derived 1 class, which extends the base class, this base class here, and this derived 2 class, which is again extending the base class. And we have kept the content of these classes to minimum because we just want to illustrate how virtual functions work. So in the base class, we have a function called show, and it just displays the message base whenever this show function is called. Don't worry about this virtual keyword here. And again, in the base class, in the derived class, we have a method or function called show, and it displays derived 1 whenever we call this function. And then again, in the derived 2, we have a method called show. So if you remember, this is called overriding base class methods. Means we have the show method in the base class. Here we override the show method in the derived class, and we also override the show method in derived class. Okay, that's fine. What we try to do now, in the main function here, we create objects from derived 1 class and derived 2 class. So you just define 2 objects. The first object is derived 1 or dv1, and the second one is called dv2. And then we create a pointer called ptr. Okay, this is a pointer because we use this star symbol here. And this pointer, excuse me, this pointer belongs to the base class. I mean, the type of this pointer is base. Now let's see what happens. As you know, pointers hold addresses of another variables. In this case, this pointer will be assigned the address of this derived class. So how do we do that? We use the ampersand operator, and we say that ptr is equal to address of dv1. dv1 is the object here. This is a perfectly valid statement. You can do it in C++. So what we're doing here, we are assigning the address of an object to a pointer. Okay, so the only thing here to understand is that this dv1 object is of type drv1, which is this class here, and this pointer is of type base. So compiler is perfectly happy here. It will allow this statement. So what happens now? The interesting thing comes now. When we call the show method on this ptr object, okay, on this ptr pointer, so we say ptr show. What show method is called in this case? See, ptr is of type base. Okay, so and base class has this show method. So should it call this method, or should it call this method? Because ptr is now pointing to the derived 1 class object. So what do you think? Similarly, in this case, we make ptr point to the address of this dv2 object. And again, we call the show method on this. So the question now is, what is the output of this program? The first option is we print base, or we print dvr1 or dvr2, because ptr is now pointing to derived one class. So when we call the show method, it should call the derived one's show method, and when it's pointing to derived two, it should call the derived two's shows method. But don't confuse yourself with what's happening here. I mean, this is the way how C++ is designed to behave. But as the designers wanted to resolve this ambiguity, if programmers do this kind of functionality, then they needed to really fix which show method should be executed here. Okay, so in this case, the output is going to be this one. Okay, the output is going to be this one. So this ptr show would give a call to this show method, and this ptr show would give a call to this method. Well, you need to appreciate that these two statements are exactly the same, ptr show and ptr show, and however they give a call to different methods. Okay, this is a really powerful mechanism which allows you at runtime to control which function get called. The reason why this derived one and derived two show methods get called is because we use this virtual keyword here. If we omit the virtual keyword from here and we just have void show, in that case we will getting this output. We'll be getting this output. Okay, so what it means is that this virtual keyword allows us to decide at runtime which function gets called based on what kind of object the pointer is pointing to. Okay, so with this example you kind of understand what virtual functions help us to do. Okay, so the question now is, why do we need virtual functions? Okay, so the classic example is when you have a base class called shape and concrete shapes that derive from it. So each concrete class overrides a method called draw. So we have the shape class and it has a draw method, and some of the other classes which extend the shape class are here. So for example, line, triangle, rectangle, and circle. As I said in the beginning, these topics are also related to object-oriented programming. That's why we are talking about classes and inheritance here. Okay, so I'm trying to answer why we use virtual functions. Okay, so imagine you have this class hierarchy where you have this shape class and it has a method called draw, and some other class is called line extends this shape class because line is a shape, and we can say that public line and then it extends shape class. Similarly, triangle extends shape class, and rectangle extends shape class, circle extends shape class. And imagine this program is part of a graphics application where when you call, for example, draw method on a line object, and this draw method draws a line on the screen. Similarly, this triangle's draw method would draw a line on the screen. However, if somebody calls the draw method of a shape, we really do not know what to draw on the screen. So this draw method is actually for the completion of the concept here. I mean, because every shape should be drawable, so that's why we include this draw method here. However, we really do not know if somebody calls this draw method on an object of the shape, what should be drawn on the screen. Okay, so what happens when we want to override a certain behavior for our derived class? So we are overriding this draw method in the derived classes rather than the one implemented for the base class. Means we're talking about the draw method, and you want to do so at runtime through a pointer to the base class. What does that mean? Let's see an example. So we have this shape class here, and then we create an array of pointers, Okay, we create an array of pointers, means this array will hold the addresses of different objects. Okay, like an array contains a set of values, similarly this is an array of pointers, so it will hold a set of addresses. Okay, so the first address it holds, for example, is of this line object. So line obj, for example, is an object of this line class, and then the second item of this array is an object of triangle class, address of the triangle class object, and then an address of rectangle class object, and an address of circle class object. So this is how this array of pointers is defined. Next, what we do, we set up a for loop. Okay, imagine we want to draw 4 pictures, 1 2 3 4. So this loop will run 4 times, and then on this base pointer object, on this array of objects, okay, we call draw method. Okay, remember the type of this base P is shape, and then this has a draw method. If you remember the previous slide, we also had the show method there, and in the base class. So what happens if we make this draw method virtual? This would end up calling the draw methods of these derived classes, which is very powerful functionality. So the above is a good example of I need to just stop this somehow, turn camera preview off. Oh, I can just stop it now. So the above is an example of open closed principle of the famous solid design principle. I'm not going to talk about these things here. You can look on Wikipedia what does that mean. Okay, so this closely relate to how software development practices are done in the industry. Okay, so this is a very powerful mechanism in the sense that this pointer allows us to call different methods that belong to different classes. Okay, you can try this in a program, and then you will appreciate why virtual functions are useful. All right. So related to what we just saw in the previous couple of slides is the concept called late binding. Okay, you just saw that we can create an array of pointers. This is an array of pointers, and it holds addresses of a set of objects. Okay, and then on this pointer we can call different draw methods. So at runtime, and imagine this array has like only 2 objects. For example, at runtime we can decide which draw method would be called based on what object this pointer is pointing to. For example, the 0th element of this array is the address of a line object. So when I is 0, this becomes 0. So it means this base pointer would draw a line on the screen, because it will call the draw method of the line class. And the second object is a triangle. The second item of this array is the address of a triangle object. And in that case, when I is 1, so it would end up drawing a triangle on the screen. So you may wonder how the compiler knows what function to compile. So in this case, although this statement says that here we are going to call a function, but we really do not know what function would be called. Okay, so what function would be called is decided based on the contents of this array, or to what address the pointer is pointing. So what happens at runtime, when it is known that the class is pointed to by base P, the appropriate version of draw will be called. So this is called late binding or dynamic binding. Okay, so late binding means when the program is actually executing, then only we decide which version of draw will be called. And choosing a function in the normal way during compilation is called early binding or static binding. Okay, late binding requires some overhead but provides increased power and functionality. Okay, so this was a concept related to polymorphism or virtual function. The next topic we have is called abstract classes and pure virtual functions. This is again related to the example we talked in the previous slide. So if you look at this class hierarchy, we have a class on the top called shape class, and then we have some derived classes here: line, triangle, rectangle, and circle. And this class hierarchy really makes sense because line is a type of shape, triangle is a shape, if you remember, this is a word, it relates to inheritance. And we also have this overriding behavior here. We are overriding the draw methods in the derived classes also. So in the class hierarchy shown, we'll never make an object of the shape class. We'll only make specific shapes such as circles and triangles. Okay, that's fine. When we will never want to instantiate objects of the base class, we call it an abstract class. So in this case, the shape will serve as an abstract class. Means when we do not really need to create objects of a class, we call it an abstract class. Okay, such a class exists only to act as a parent of derived classes that will be used to instantiate objects. Okay, how can we make it clear to someone using our family of classes that we don't want anyone to instantiate objects of the base class? That's a good question. I mean, when someone sees this class hierarchy, they will also try to create objects of the shape class. However, here this class only serves as a template. I mean, it helps us build a class hierarchy, or it serves the meaning in terms of object-oriented programming. So, but how can we ensure that someone doesn't create objects of the shape class? Because if someone create objects of shape class, they may try to call a draw method, and it will not do anything there. So how can we ensure that? Excuse me. So we can do that by placing at least one pure virtual function in the base class. So what is this pure virtual function? Okay, that's fine. A pure virtual function is one with the expression equal to 0 added to the declaration. So for example, if you have this base class base, and you have a method called show, return type is void, and this is a virtual function, that's fine. But if you add this equal to 0 semicolon at the end, this becomes a pure virtual function. Okay, once you have a class definition that contains a pure virtual function, this class becomes an abstract class, and you cannot create objects of this class. For example, here in the main, if you try to create an object of base class, this is the base class and the name of the object is bad, you can't do that. Compiler will complain. So this class only serves as a template for the other derived classes, and this is the only way to enforce that you can't make objects from this class. All right, so in this slide you learn two aspects of object-oriented programming in C++: what is a pure virtual function and how to make an abstract class. So in this class hierarchy, for example, this shape class would have this draw method as pure virtual function. Okay, so you would say virtual void draw equal to 0. All right. So, however, you can see that other classes, derived one, are happy to extend this base class. Okay, and they are supposed to implement this show method here. Okay, and that's one of the requirements. If some class is extending a abstract class, they are supposed to implement their methods here. All right. So this example is a bit more realistic. Okay, I feel that if you look at this example, you will appreciate how abstract classes and pure virtual functions are more useful, in the sense that you can, I mean, from your coursework's perspective also, this can be useful. So we have this class called person. It has a data member called name. Every person has a name, that's fine. and then we have some methods here. So get name, when you call an object of this person class, would read the name into this name data member. So C in name, and we can also have a constructor here, but it's just this is just for the demonstration purpose. And put name would print the name of the user of the person. And then we have this get data and is outstanding. These are two pure virtual functions, you can see. Okay, so these are two virtual functions here, and this person class is extended by the student class and also extended by the professor class, and these two classes extend get data and is outstanding methods here. Okay, so what does get data do? Get data would call get name, and it would call get name, and outstanding would return this GPA, and outstanding is outstanding in case of a professor would return number of pubs if greater than 100, true, false. Okay, and get data would again call get method for the professor, and it would also ask for number of professors publications. So this numpubs is publications is about number of research articles somebody has, and this is hold under this data member called numpubs, and for the student GPA is hold under this GPA variable. So what's happening here? This person class becomes an abstract class because this has two pure virtual functions here. Okay, because every student is a person, that's why we are kind of building a class hierarchy here to satisfy our object-oriented principles, and every professor is a person, that's why we are doing it. And this professor shares some functionality from this person class. What is that functionality? Get name. Okay, get name function is called among under this get data function, okay, which is a pure virtual function. Okay, and inside the main function we can create an array of pointers. Okay, this is an array of pointers, okay, of class person. Okay, person is the base class if you remember, and then we set up a for loop and then enter student or professor. So enter student or professor, S for student, and then enter name. Then we call this is perspective PTR. Sorry, this is person PTR, and then n is initially 0, so we are referring to the first pointer. And then we create a new student if the choice is S. Else if the choice is maybe a P, then we create a new professor, and this is happening at runtime. And then if we call the get data member function, you would see that this member function would be called based on what kind of object this pointer holds to. Okay, get data for person, and this is an interesting functionality. Okay, so you can have a look at this program and maybe also try to run it. Okay, virtual base classes. Well, virtual base classes are something needed when we have issues with multiple inheritance. So before leaving the subject of virtual programming elements, we should mention virtual base classes as they relate to multiple inheritance. So when the child, so if you look at this class hierarchy, in this we have this base class and two classes, child1 and child2 inherit some functionality from this base class, and we have another class called grandchild, and it extends from these two classes. Okay, how does this happen? You can define this parent class like this, and imagine we only have one data member here, and then you can define this child1 class by saying public parent, because child1 is extending parent and child2 is also extending parent, so you can say child2 public parent. We haven't included any content in these classes because we just want to demonstrate some functionality here. And grandchild publicly extends child1 and child2, child1 and child2, And yeah, so in this case, when the child1 and child2 classes are derived from parent, each inherits a copy of parent. So each inherits a copy of parent, and this copy is called a sub-object. Each of the two sub-objects contain its own copy of parent's data, including base data. Now, when grandchild refers to base data, which of the two copies will you access? I mean, will it access? What I said, child1 and child2 get a copy of base data. Okay, so they have a copy of base data, and grandchild extends these two classes, so it will get two copies of base data. It means it will be having two declarations of this base data, which isn't correct. Okay, so this is ambiguity, and this is a situation of ambiguity. Actually, how do we resolve it? So in this arrangement, a problem can arise if a member function in the grandchild class wants to access data or functions in the parent class. Okay, so what happens here? Get data. So if someone calls get data on an object of grandchild class, it says return base data. Okay. However, grandchild has two copies of base data. One is coming from this side, another is coming from this side. So which one are we referring to? A compiler error occurs when the get data member function in grandchild attempts to access base data in parent. Why? Because there are two different paths to have this data member. So how do we remove this ambiguity? So we make child1 and child2 into virtual base classes. Sorry for the grammar problems here, spelling problems here. So what we do, we make a small change. We say that child1 virtually extends parent. We add this virtual keyword here and also the virtual keyword here. We do not make any changes to the grandchild. The use of the keyword virtual in these two classes cause them to share a single common sub-object of their base classes, of their base class parent. Since there is only one copy of base data, there is no ambiguity when it is referred to in grandchild. So just remember, you need to use this virtual. Well, here you can see that when we use multiple inheritance, we can have complications. And we might have to deal with multiple copies of the objects, sub-objects. So it's always recommended to keep the use of multiple inheritance to the minimum. So, and that also makes your programming more easier to understand and less error prone. And one more thing I would like to highlight here is that Java, just because multiple inheritance can be complicated, Java doesn't use multiple inheritance, which is in its own is a great feature. Okay, static functions is a small topic. I will just introduce it to you. I'm sure it will be useful for you. As you may recall, a static member is not duplicated for each object. I mean, we talked about in week 9 lecture classes and objects, slide number 34. A static data member is not duplicated for each object. What does that mean? Rather, a single data item is shared by all objects of a class. So for example, if we have a class called foo and it has a member called count and it is of type static. Okay, and we create objects of foo, 3 objects, f1, f2 and f3, and if we try to print the value of this count for these 3 objects, we'll get the same value. The reason is that we only have one copy of the static data members. Well, you may argue that we have 3 different objects, they should have 3 different copies of this count data member, but that's not the case. If we remove the static keyword from here, in that case, this count will have, each of these three objects will have three separate copies of this count, and they will be independent of each other. However, when our data member is static, in that case, all the objects share a single copy of the data member. You can look at this program and then try to understand what we are trying to do here, but I wanted to say that when we have static data members, they have only one copy for all the objects. Now, this concept was about data members. We can extend this concept by showing how functions as well as data may be static. Okay. So in this program, there is a static data member. There is a static data member, total. Okay. In this class called gamma. This data keeps track of how many objects of the class there are. We're going to create objects of this class, and then this member will keep an account of how many objects are there. It is incremented by the constructor and decremented by the destructor. So if you see this is the constructor of the gamma class. So constructor means whenever we create an object, the constructor get called automatically, and in that case we increment this total by 1. So it means this will keep a track of how many objects are being created. And in addition, we have this non-static data member, and this is used to assign a sort of ID to all objects, and every object will have a separate copy of ID. So each time we create a new object, we assign total to this ID. It means initially total is 0. When we create the first object, this will become 1, and the ID of the first object will become 1. And then when we create another object, we call this constructor again, because total is shared among all the objects. Total will become 2, and the ID which is not shared will become 2. Every object will have a separate ID. However, the value of total would be same for all the objects. All right, that's great. The interesting thing here to note is that we also have this static member function called show total. Okay, that's interesting. We haven't seen any member function yet which had this static keyword here. So this is interesting. We'll understand how we call the static member functions, and then we also have this show ID. To display this total, which is a static data member, we have a static member function, and then to display this ID data member, we use this simple member function called show ID, which is not static. Okay, let's see what happens now. And if you remember, static data members are initialized outside the class. So total is a static member, so we initialize it to 0. Okay. What's happening in the main function? We create an object G1 of this class gamma, and then we call, what's happening here? What's this statement? Name of the class followed by scope resolution operator followed by a function called show total. Well, that's interesting. Okay, so when this statement is executed, this would print 1. So this would print total is 1. Okay, that's interesting, because when this first line is executed, the constructor would be executed and total will become 1. That's interesting. When this line is executed, this constructor would be executed 2 times and total will become 3. And when this line is executed, it will say total is 3. Well, you might be questioning, how can we call a function like that? Okay. This is a perfectly valid statement. Okay, in this case, we are calling a static data member static member function of gamma class. So because show total belongs to this gamma class, we use the name of the class followed by show total. Well, some people will argue here that member functions could only be called on objects using the dot operator. For example, here, name of the object followed by dot operator and the name of the function. Well, this functionality is available only to non-static member functions. However, the static member functions should be called like this. The reason is that static member functions do not belong to any object. Okay, so static member functions or data are like they are shared by all the objects, so they shouldn't be sticking to any specific objects. So this is more natural way of calling them. Here I say that, however, this won't work if show data is a normal member function. This statement wouldn't work if you remove the static keyword from here. In that case, it would become a normal member function. An object and the dot member access operator are required in such cases. To access show total using only the class name, we must declare it to be static member function. This is what we do in this program is called stat func in the declarator. So that's how we do it. Well, this is an interesting functionality, and then whenever we call show total, it gives me the number of objects that we have created of this gamma class. And again, whenever we call it later after creating more objects, it gives me the number of objects that we have created without even worrying about which object, without worrying about the dot operator and then the way we call the other member functions. Alright, so this was about static member functions. You can see that you can create static data members and static member functions also, and there's a different way of calling static member functions. This is the last topic. Yeah, I think so. Yeah, the this pointer. This is very important, and you might have already seen this pointer in Java. Okay, what is the use of the this pointer? The member functions of every object, have access to a sort of magic pointer named this, which points to the object itself. So if you have this, so this is a keyword and this refers to the object itself. Thus, any member function can find out the address of the object of which it is a member. What does that mean? Let's look at this program. Class called where has a data member, this array of type char, and then a function called reveal, which prints my object's address is this. We haven't defined this anywhere here, but this is actually a magic pointer, as I said, and it holds or refers to the address of the object. So this is not defined anywhere, but we can use it like this. So when we define objects of where class, the first is w1, w2, w3. On w1 I call reveal. So my object's address is, it will print the address of w1 object, and this will print the object of w2 object, and this will print the address of w3 object. Okay, so yeah, so that was a short introduction to this pointer. How can we access data members using this pointer? Okay, so in this class we have this the name of the class is what, a data member called alpha. Okay, a sample function called tester. So in this case we can say that this alpha is equal to 11. Okay, and this is same as alpha equal to 11. Okay, so this pointer can be treated like any other pointer to an object, and can thus be used to create the data in the object it points to. So this statement is same as this statement, but some people prefer using it without this pointer, and some prefer it with this pointer. So here you can see we have an object w of what class, and on this we call the tester function. So when this tester function is called, this would be executed, and in this case this pointer is referring to this w object and this w object's alpha data member, and we set it to 11, and then we print this value as well. Okay, so this was an example on how we can create how we can access data members using this pointer. Polymorphism. So whatever we saw in previous slides is example of polymorphism. Polymorphism refers to the ability to associate multiple meanings with one function name, okay, using the mechanism called late binding. This is a very powerful concept, okay. Polymorphism is a key component of the philosophy of object-oriented programming. All right, so this keep this thing in your mind. And this is another interesting example I like about polymorphism. Imagine you are building a class hierarchy, and on the top you have the base class called animal, and because animal speaks or makes sounds, and from this animal class we can make another or derive another class called cat, and it makes a sound like meow, and dog makes another sound called, let's say, woof. So in order to build this class hierarchy and to understand polymorphism, we can say that this class is animal, and then we define this virtual function animal sound or speak, okay. So what happens, this is a generic function, of course, and any class that is extending the animal class would need to override this member function. And then what happens when we create an object, when we create a pointer of the animal class and make that pointer point to an object of dog class, and then we call animal sound function on this object, we will call this dog class animal sound. And imagine if this pointer points to a cat class object and then we call animal sound on that, it would call the cat class animal sound function. All right. So finally, the summary. Virtual functions provide a way for a program to decide while it is running what function to call. Okay. Virtual functions make possible greater flexibility in performing the same kind of action. Means the pointer was holding an array of, we had an array of objects and we were doing the draw method, okay. So this is the same kind of action on different kinds of object. And this is an example of polymorphism. The use of one or more pure virtual functions in a class makes the class abstract, which means that no objects can be instantiated from it. A static function is one that operates on the class in general. Okay, that's why we had the class name and the scope resolution operator, rather than on objects of the class. In particular, it can operate on static variables.